Hi guys. So here's 13.2 sine and cosine ratios. So our essential question, how can you use the sine and cosine ratios and their inverses in calculations involving right triangles? Now sine and cosine is the other two trig ratios that you're going to learn. We already learned tangent, so these are the other two. So our shortest answer is basically, well, given the measure of one acute angle, so again, that's known as a reference angle. So let's say reference angle A would be a reference angle. Okay, that's basically what it means. And the length of the hypotenuse, okay, so we're definitely using the hypotenuse here. You can use the sine and cosine ratios to find the lengths of each leg. Oh, so we're using one of these legs, could be this one, could be that one, but we're definitely using the hypotenuse for both of them. So that's basically what it's trying to say. And then we use the inverses to find the angle measures. So there is that situation where we could find the inverse and we could get the angle measures if we need to. All right, so example one, sine of d. Now sine is basically, its definition is the opposite over the hypotenuse. And there's my pen doing its thing again. All right. So again, we're going off of D for our acute angle. It's so cute. All right. But basically, that's our reference angle. Now, on the opposite side of him, of that angle, we have EF, which happens to be 8. And then the hypotenuse is always on the opposite side of the 90 degree, the right angle. Okay. It's the largest line segment of a triangle, of a right triangle at least. All right, which is 17. So there's my sine ratio for angle D or vertice D. Now, cosine of D is adjacent. Okay, it's the adjacent leg over the hypotenuse. So cosine D is our reference angle, except now we're using the adjacent next door neighbor, which is 15. All right, DE. And then over the hypotenuse, which again, the hypotenuse is always on the opposite side of the 90 degree angle. And there you go. Now, sine of F, okay, is our new reference angle. Let me change a different color. Ooh, purple. Haven't used purple ever. There we go. All right, sine of F, so there's our reference angle. And then sine, again, is going to be, always going to be opposite over hypotenuse. So the opposite of F is 15. And then the hypotenuse, again, is always on the opposite side of the 90 degree angle. 17. There we go. And then lastly, cosine of F. Let me use, blue. Yeah. So again, reference angle there, F. Cosine is the adjacent over the hypotenuse, always. And his adjacent is 8, right, EF. And then the hypotenuse, once again, is always on the opposite side of the 90 degree angle. And there's your ratio. Now, reflective question. I know I didn't write it, but what do you guys notice between, okay, that was a terrible little mistake right there. What do you guys notice from the cosine of angle D ratio to the sine of F and its trig ratio? And then what do you guys notice here? Okay, and that's because they are considered complementary. So this is considered complementary. If one of your ratios doesn't do this, then something's wrong. You did something wrong. All right. So those are complementary angles because if, for example, D was angle 30 degrees, all right, if then 60 would have to be, or I'm sorry, angle F would have to be 60. They both have to add up to 90. They have to be complementary. And that's why the ratios have that in common to each other. So just study that, for example. Notice the pattern that it forms. All right, your turn number one. Find sine of A and then find cosine of A. All right, trigonometric ratios of complementary angles. If angle A and angle B are acute angles, so cute, in a right triangle, then sine A equals cosine B, and cosine A equals sine B. So what's interesting here is that's already what I showed you there. All right, notice how sine D equals cosine F, and cosine D equals sine of F. Okay, you guys notice that pattern? That's what they're talking about. So basically, what we're doing here is if we have some angle given to us, like from angle A, all right, let's say 30 degrees, for example, um, then basically all you have to do is, well, we know that if this is 90 degrees, a right angle, and the sum has to be 180, well, that means this missing piece here has to be 90 minus the 30 from A, and that'll be 60. Okay, they're complementary. Okay, that's because they both add up to 90. All right. So basically, if you have cosine of, or if you have sine of A or sine of theta, which is 30 degrees, and cosine of 90 minus theta, which again was 30 degrees, which should be 60, will be the same as sine of 30. That's what they're saying. And we're going to prove that coming up next. So that was another example right there. All right, so example 5, given that sine of 38 degrees equals approximately this ratio, write the sine or the cosine of a complementary angle. So again, keywords, complementary angle, in terms of sine of 38 degrees. So what that means is we have to find the cosine of the complementary angle. So we have 38 degrees, splendid, but cosine, again, of 90 degrees minus theta. Theta is that angle right there, 38 degrees. So basically, cosine of 90 minus 38, you should get what, 52? Let me double check. It's a little late. 90 minus 38. Yep, 52 degrees. All right. Uh, type in your calculator. I think for you guys, 52 cosine, and you get approximately, let's see, 0.61566, but looks like they rounded up, so yeah. So notice how the ratio should still be the same. But this is how you write the complementary angle for cosine. So this is really what they were really freaking out about. So if they have that on a test, be sure to show that setup. All right, your turn number 2, cosine of 60 degrees. So there's your theta. And it gives you that ratio right there, 0.5. Now they want you to find the sine of the complementary angle. So here's my only hint that I'm giving you, right? And then you do the rest. All right, so now application of this. There's actually a permitting law for ramps and stuff like that. Um, for any wheelchairs or any ramp in general, especially in California. I think our state standard for this is like 8.5 degrees of a gradient. Here they have 11 degrees for their ramp. But yes, they literally have to have a certain degree for their ramps. If not, they can get a fine for it. And then you see guys with pickaxes and those concrete sledges and the whole bit, and they'll tear it up and redo it just to make it city code. It's pretty crazy. But you have a 12-foot ramp here. Okay, sweet. So that's our hypotenuse. Very nice. And basically, we need to provide some additional steps, providing the wheelchair access to the library. Okay. The ramp makes an angle of 11 degrees, so that's our theta. Okay, theta, our angle. Okay, with the ground. So there's the ground, and then, again, 11 degrees incline. Now find the dimensions to the nearest tenth of a foot. So that means we have to solve for uh, x and then solve for y. So we have to figure out how tall this thing needs to go up on this wall, and then how much length do we have to give on the floor, which will be our y. So let's go ahead and start solving for those. I'm going to solve for x first, just cause. All right. So basically, it's this. We know the 11 degrees. We have the hypotenuse, and again, we have our theta. All right. Now, what is x in terms of theta, our 11 degrees? That's the opposite side, right? And then y is the adjacent. So notice how our reference angle is the 11 degrees, the gradient, or the theta, okay? So solve for x. We know that, let's see, sine of 11 degrees will equal the opposite, which is x, over the hypotenuse, which is 12 feet. So how do you get rid of dividing 12 feet? Multiply. So x should equal 12 times sine of 11 degrees. Now in your calculator, you'll have to type 11 sine equals, okay? And if you do that, you should get um, 0.1908, blah, 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 right? And then multiply that to the 12. All right, so it looks like for x, we got 2.289 feet. Okay, we have feet because, again, our hypotenuse was given in feet. So that's how tall the wall needs to be for that particular ramp. Now, your turn number 3, this is how I know if you're actually listening or not. Your turn number 3, I want you to solve for y. All right. And I already kind of gave you a hint earlier on what y is to theta. So that should kind of cue you into where to go. All right. Inverse of sine and cosine, basically finding the angles. So let's say if I want to find angle P. All right. Now, looks like I can't find angle P unless I got my opposite side. So looks like we can actually find for angle R first. All right, so let's go ahead and find for angle R. Now, 7 is given, and that seems to be on the opposite side of our vertice R. And then our hypotenuse ends up being 13. So we're using opposite over hypotenuse, so that is sine. All right, so let's see. We can do this. We can do sine of our reference angle, R, which equals the opposite over hypotenuse, which is 7 over 13. Now, the inverse and how inverse works is basically once you get that, this is the setup. To get rid of the sine, you have to use the inverse. So on your calculator, that's what that looks like. So you're going to type 7 over 13, or 7 divided by 13, press second, and I think it's sine, and you'll see the sign with a -1 up there for that. And you should get, so again, you're doing this, and you should get approximately 32.578. Now, be careful on some problems. They might say just to round to the nearest, so just see if you have to do that or not. All right. Sometimes I think some of the problems in your book might say to round. So if they say round to the nearest, you would just say 33 degrees. Now, what's kind of nice is if you know that angle R is 33 degrees and that angle P and R have to be complementary, you could just do 90 minus 33 and be done with this. You would find angle P 57 degrees. So that's how you could figure out the angles for those situations that arise. All right. So notice how I use sine only because the adjacent they didn't give you that, right? Now, could you have found the adjacent? Yeah, you could have used Pythagorean, right? So 13 squared, get 169 minus the 49 because of 7 squared, you get 120. Square root that gives out to be a crazy radical. Um, but yeah, you could have totally done that. All right, but again, just use what they give you, and that'll take care of most of your homework. Speaking of which, there you go. Page 703 through 704, numbers 1 through 16. And check this out. You could tell the boy is like not even focused right now. He's just like, whatever. Even his body language just says, I'm not really paying attention. And then this girl just comes out and just wrecks his face. Look at that. Look at that. He's just like, yep, I wasn't paying attention. Yep. All right. Have a good day, guys.